Hello everyone, my name is Junhao Dong. I am presenting our CVPR paper this year, Adversarially Robust Future Learning while Parameter Co-distillation of Similarity and Class Concept Learners. In this paper, we analyze two widely used robust future learning paradigms, visual similarity learning and class concept learning. We show their complementary properties, and we further propose a new method to unify these two learning schemes for an improved adversarial robustness. And adversarial examples, they are tailored inputs designed to confuse neural networks. Although these adversaries appear visually similar to natural examples, they can cause significant disruption during the inference stage. For instance, by adding an undetectable perturbation to an image of a panda, we can create a corresponding adversarial example that causes a high confidence misclassification. Technically, this example can be obtained through image-level gradient ascent. Currently, adversarial training is one of the most effective defenses against adversarial examples. In the context of classification, adversarial training aims to build a robust model that not only accurately classifies clean samples, but also withstands adversarial perturbations. This is typically achieved by solving a minimax optimization. But however, adversarial training often requires extensive data, limiting its practical application, especially on the few short cases, and this paper addresses adversarial robustness in such data-constrained scenarios. And existing methods can be categorized into similarity learning and class concept learning. Similarity learning relies on class-wise feature mean prototypes from the support set to predict the corresponding query cell samples by measuring feature-level distances. However, it's limited to a restricted label space such as 5 or 10 classes. In contrast, class concept learning optimizes parameters of a global classifier across the entire data distribution, learning from the semantic categories of all training data. Thus, these two paradigms lead to adversarial robustness from distinct viewpoints. To support this claim, we provide feature space visualizations for visual similarity and class concept learning. The key observation is that similarity learners often spread features of a certain class into multiple classes with potential overlaps. In contrast, class concept learners produce more distinct class-wise classes separated by the decision boundary. And robust accuracy further confirms that similarity and concept learners are affected differently with respect to perturbation radius. To leverage the strengths of both models, we propose a simple and effective method, dynamic parameter level interpolation. By co-distilling parameters from both similarity and concept learners, we update the unified model by the momentum mechanism focusing on the embedding part to handle label space differences. And direct parameter distillation might lead to inconsistencies due to label space discrepancies. We thus introduce cross-branch global adversarial perturbations as an initialization to guide adversary generation, which can be regarded as an effective adversarial perturbation across all the samples in a certain category for the unified robustness. And note that during the training stage, similarity and class concept learner exhibit different robustness characteristics. We thus introduce a robustness harmonization module that adjusts the learning rate of the less robust learner to balance contributions and prevent one module from dominating the whole distillation process. This is also quantified by relative adversarial robustness scores based on KO divergence ratio. And here our experiments across various few-shot settings like 1-shot and 5-shot demonstrate the effectiveness of our method. And here we compare robustness against different attack strengths. Our method consistently outperforms others, showing that our unified model maintains robustness across various perturbation strengths. Although our training process is computationally intensive since we include like 2 learners during the distillation process, we can still improve the training efficiency by using the single-step strategy. Our method shows also excellent cross-domain transferability, maintaining high accuracy and robustness across different domains. And ablation studies also validates the effectiveness of each module and the co-distillation components. And here we also provide TSNE and also grade CAM visualizations to illustrate the clear decision boundary achieved by our method. To sum up, our contributions include a novel adversarially robust future learning framework through parameter co-distillation, cross-branch adversarial perturbations, and a robustness harmonization module. Comprehensive experiments demonstrate the effectiveness and generalization ability of our method. We can also obtain further efficiency improvement via single-step adversary generation strategy. And that concludes my presentation. Thank you for your attention.